Hello everyone, this is Sun from Waseda University. I would like to introduce our work, Learned Image Compression with a Fixed Point Arithmetic. So this is a joint work with Professor Lu Yu from Zhejiang University and Professor Jiro Kato from Waseda University. So first is the introduction. Learned image compression, we call LIC, is actually composed of several components. So first we have an encoder, neural network encoder, which can transform the original input X, which is original RGB image, to a latent code Y here. And then we will use a quantizer to generate Y hat, integer Y hat here. So for this integer Y hat, we can use arithmetic encoder to generate a bit string. And then in the decoder side, so we can use arithmetic decoder to recover this Y hat. And finally, we will use an decoder, neural network decoder, to generate a reconstructed image X hat here. So usually all these frameworks, it is based on the floating point arithmetic. But there are two problems for this floating point arithmetic. So first problem is round-off errors. A floating point arithmetic may cause round-off errors during decoding when encoding is done on a different platform. So for example, if we do the encoding on the CPU and do the decoding on the GPU, so this round-off error might happen, and such error will propagate catastrophically in the entropy decoding. So as a result, so you can see in this figure, so the decoding will be incorrect. And so the second problem for the floating point arithmetic is a huge memory and computational cost. So compared with 8-bit fixed point, so 32-bit floating point will consume 4 times larger memory cost since this is 32-bit while fixed point is only 8-bit. And about the computational cost, as shown in this figure, so for the addition, so 32-bit floating point may consume 30 times higher energy since one is 0.9 and one is only 0.03. And about the multiplication, so 32-bit floating point may consume 18.5 times higher energy since 1 is 3.7, but fixed point is only 0.2. So in order to solve these two problems, so in this paper, so we will make a learned image compression framework with a fixed point arithmetic. And in detail, so we have two proposals. So first is the analysis synthesis fine-tuning scheme. So before introducing this scheme, so we will introduce how to do the scaling and quantization. So scaling here means that so we will scale the weights to a certain range, from minus alpha to plus alpha. And this scaling is performed in groups, which means that so for the weights W are in one group, so all these weights in one group will share one scaling factor, and this scaling factor actually is just a scalar. And so we can generate this scaling weight like here. And in order to ensure that so this scaling vector can be scaled to this certain range, so this scaling factor can be calculated by this equation. And after getting this scaling weight, and so we will do quantization. So actually, so this Q can be linear or nonlinear quantization. So this slide will give the quantization laws for the LIC. So in this paper, so we will use a hyperprior network, which means that so we have a analysis transform. So we have 4 layers in the analysis transform and 4 layers in the synthesis transform. And we also have hyperpaths here, HA and HS. So if we quantize the analysis transform and the synthesis transform, so there will be some coding loss as shown in this table. So originally, we have RD cost. So here, this original means that without any quantization. And so if we quantize each layer in the analysis transform and the synthesis transform, so you can see that the RD cost will becomes larger. So larger RD cost means that so there will be some coding loss here. And so in the analysis transform, so we can see that the quantization loss for the final layer is largest, and for the synthesis transform, the coding loss for the first layer is largest. Therefore, so we will try to fine-tune this layer in the synthesis transform and this layer in the analysis transform. So we give two fine-tuning schemes. First is the individual fine-tuning, which means that so we will just fine-tune the context layer individually. So as shown in this figure, this blue bar is origin, means that without any quantization, so we have RD cost here. And after quantization, so we have RD cost. So you can see obviously, so this red bar, this RD cost is larger than the origin. So we first individually fine-tune this layer. So and then after this fine-tuning, so you can see that the RD cost becomes much smaller, which means that the fine-tuning works for this GA3. However, for the GS0 here, after the fine-tuning, so this green bar, although the RD cost is smaller than this red bar, but still you can see the result is larger than the origin. Therefore, so we can think that the quantization loss for the analysis transform can be reduced by this individual fine-tuning. However, the quantization loss for the synthesis transform layer cannot be reduced so much by this individual fine-tuning. So in order to reduce the quantization loss for the synthesis transform, so we try to jointly fine-tune the synthesis transform with one analysis transform layer, and the fine-tuning result is shown in this figure. You can see that this is the individual fine-tuning result, and these four are the jointly fine-tuning result. So you can see that especially this case, so which means that so we will fine-tune this first layer in the synthesis transform GS0 together jointly with this GA3, which is the final layer in the analysis transform. So after this jointly fine-tuning, so the RD cost is this value, which is smaller than this value, which is the individual fine-tuning. So based on this observation, so we think that for the synthesis transform layers, so we would like to use the joint fine-tuning to reduce the quantization loss. However, for the analysis transform layer, so we can utilize the individual fine-tuning to reduce the quantization loss. Therefore, so the proposed fine-tuning method is that so we will first jointly fine-tune the synthesis transform layer GS sequentially, means that so first we will quantize and jointly fine-tune this first layer in the synthesis transform with the final layer in the analysis transform, and then so we will quantize the second layer in the synthesis transform and also fine-tune jointly with this layer, this third layer in the analysis transform, and then go to the next synthesis transform layer and the final synthesis transform layer. So after joint fine-tuning all the synthesis transform, so then we can start fine-tuning the analysis transform. But for the analysis transform, so we just individually fine-tuned analysis transform, since we think that all the synthesis transform is already fine-tuned, and then so the weights in the synthesis transform is fixed. Therefore, we only individually fine-tune the analysis transform sequentially, so from the first layer until the final layer. And then we go to the second proposal, which is the LUT-based CDF model. So for the Y, so Y is the output of the analysis transform. So we will have a coding probability. So in fact, each feature sample Yi is assumed to be a Gaussian distribution with a mean and scale. So this mean and scale, they are estimated by a Heifer decoder actually. So after obtaining this mean and scale, so we can create a probability model like this. So if we assume this is a Gaussian, so then like this. And so based on this probability model, so we can calculate the probability for the Yi. So here the probability is defined as the probability from Yi hat minus 0.5 to Y hat plus 0.5. So this area is considered as the probability for this Y hat. So then, so based on this probability of Yi hat and this Yi hat value itself, so we can use arithmetic coder to chant the bit stream. So here, the key point is that so we can see that the mean and the scale actually can create a distribution model. But the problem is that so if the scale is a floating point arithmetic, so in some cases the decoding will be incorrect. Therefore, so we will quantize the mean and the scale to create a CDF LUT, and then based on this CDF LUT, the decoding will be always correct, regardless of the decoding platforms. So in detail, for the mean, so we will do a linear quantization, and the precision is 0.125, and the step is 8. And for the scale, we will make a range for this scale, and the minimum range is 0.01, and the maximum range is 64. And we will do the linear quantization in the log field like this. So, and also for the Y hat, originally, so we have no limit for the range for the Y hat. But as you can see in the CDF, so in here, this part, so if Y hat minus mu is same, so we can share the same CDF for different mu. Therefore, here, in order to share the CDF LUT for different mean values, so we will limit the range of Y hat within this mu mean minus R to mean plus R. So this R is set as 63 for small lambda and 127 for large lambda. Then we go to the experimental results. So coding loss compared with 32-bit floating point baseline is quite small when quantizing to 8-bit. So you can see that here the green curve is the 32-bit baseline, and the yellow curve here is our proposal. So you can see this is quite small, the coding loss. And for the cross-platform coding, so we check 2 different CPU and GPU platforms and find that all these encoding and decoding are correct. And also by using this LUT-based CDF, so the coding loss is quite small as shown in this figure. So the conclusion is that in this paper, so we propose LIC with a fixed point arithmetic. and we fine-tune the analysis transform and the synthesis transform layer by layer, and also explored the LUT to calculate the CDF for mean and scale to avoid the floating point error. And the result shows that so we can indeed reduce the coding loss caused by the weight quantization, and the encoder and decoder correctly regardless of the platforms. So for the future work, we will try to quantize the activation and also explore some lower bit width quantization, such as 2, 4, or 6 bit. Okay. Thank you very much for your attention.